Welcome back. Let's talk about the relationship between the specific heat and the degrees of freedom. To arrive at such a relationship, we'll make use of the molar specific heat at constant volume. So Cv is equal to Qv by N into delta T, where Qv is the amount of heat absorbed or evolved by system at constant volume. As the process is carried out at constant volume, clearly this will only change the kinetic energy and potential energy of atoms and molecules of that system, which in turn will change the internal energy of that system. So we can replace Qv from the above expression by delta E as, so Cv will be equal to delta E by N into delta T. Let this be equation first. Now, according to the law of equipartition of energy, each independent degrees of freedom contributes an average kinetic energy of 1 by 2 RT per mole to the system. Degrees of freedom are nothing but actually the ways by which a molecule can move, that's translate, rotate or vibrate. This indicates that if the system is having one independent degrees of freedom, then that will contribute an average kinetic energy of 1 by 2 RT per mole to that system. And if it has got two independent degrees of freedom, then that will contribute obviously 2 into 1 by 2 RT per mole to that system. Therefore, for 1 mole of ideal gas having F degrees of freedom, we can write the internal energy will be equal to F by 2 into RT. Actually, internal energy is the sum of kinetic energy and potential energy, but as we have talked about the ideal gas, for ideal gas, potential energy is taken as 0 as per the kinetic theory of gases. So the internal energy will be contributed by the kinetic energy only, and that's equal to F by 2 into RT. And as internal energy is the function of temperature only, therefore delta E will be equal to F by 2R into delta T. For N moles, delta E will be equal to F by 2R into N into delta T. Now putting the value of the change in internal energy, that's delta E, in the equation first, we have Cv will be equal to F by 2R into N into delta T divided by N into delta T. This and this will go, and we are left with Cv equal to F by 2 into R. This is the required relationship between the molar specific heat at constant volume and the degrees of freedom F. Now, as per Mayer's relation, Cp minus Cv is equal to R. Therefore, Cp will be equal to F by 2 plus 1 into R, where F is the number of degrees of freedom, and this varies with the type and geometry of gas molecules. That is, for monoatomic gases like noble gases, F is equal to 3, meaning that there are only 3 degrees of freedom for such gases, and this arises due to the 3 translational motions. As the atoms can move along all the 3 directions in space, they do not have any rotational or vibrational motions. Therefore, Cv will be equal to 3 by 2 R, hence Cp will be equal to 5 by 2 R. On dividing Cp by Cv, we will get an adiabatic index, and that comes out to be equal to 1.66 for monoatomic gases. In the same way, for diatomic gases like oxygen, nitrogen, carbon monoxide, etc., or linear polyatomic gases like carbon dioxide, they have 5 degrees of freedom. And this arises due to the 3 translational motions and 2 rotational motions as shown by the arrows. Point to note is the rotational motion along y-axis does not contribute since it doesn't have the moment of inertia. Clearly, Cv will be equal to 5 by 2R, hence Cp will be equal to 7 by 2R, and the adiabatic index comes out to be 1.40. Similarly, for non-linear polyatomic gases like nitrogen dioxide, sulfur dioxide, water molecules, sulfur trioxide, etc., F is equal to 6, indicating that there are 6 degrees of freedom which arise due to 3 translational and 3 rotational motions as shown by the arrows along x, y and z directions. Therefore, Cv is equal to 3R, hence Cp is equal to 4R On dividing, we'll get the adiabatic index as 1.33 for non-linear polyatomic gases. Point to note is vibrational degrees of freedom does not contribute because they are frozen out at ambient temperatures. Now, for a mixture of gases, the molar specific heats can be calculated by the following expression, where CV1 and CV2 are the molar specific heats at constant volume for gas 1, gas 2, and N1 and N2 are the corresponding number of moles. While calculating CV mix, we can easily calculate CP mix by the Mayor's relation as CP mix minus CV mix will be equal to R. Let's illustrate this with certain examples. We have the first illustration that says, for an adiabatic process, if P is equal to V raised power X, then X is. We have the following options. Option A, X is equal to 1. Option B, X is equal to minus 1. Option C, X is equal to 3 by 2. And option D, X is equal to minus 3 by 2. Since P is equal to V raised power X, this implies P into V raised power minus X will be equal to 1, and that's a constant quantity. Now, for an adiabatic process, as we know, PV raised power gamma is equal to constant. Clearly, upon comparing the two, X will be equal to minus gamma, or X will be equal to minus 3 divided by 2. This is because gamma is always greater than unity. Therefore, option D is the correct answer. In the same way, we have the next illustration that says, calculate the molar specific heats at constant volume and pressure of a system containing 2 moles each of helium and hydrogen gas. As we have the system containing mixture of gases, clearly we can find the molar specific heat at constant volume by the following expression, where CV1 is the molar specific heat for gas helium and CV2 is the molar specific heat for gas hydrogen. As helium is monoatomic, so CV1 will be equal to 3 by 2 into R, and hydrogen is the diatomic gas, clearly CV2 will be equal to 5 by 2 into R. And each gas has got 2 moles, therefore while putting the values, we'll get CV mix equal to 2 into 3 by 2 R plus 2 into 5 by 2 R divided by 2 plus 2. And that comes out to be CV mix equal to 2 into R. Now, while using the Mayor's relationship, that is CP mix minus CV mix equal to R, we will get CP mix equal to 3R. I hope you understand this. If you like my videos, please do not hesitate to share and subscribe. Thank you.